All right. Well, let's get to it then. So, how's everyone doing this morning? Gucci. Okay, that's good. Make sure the mod view is good. Um, and looks like we're good and live. All right. So let's see. The other thing I need is from Overleaf. All right. So we're going to start talking about. We talked about sequences last time, and file. We're going to continue to talk about sort of a um, special set of sequences. Okay. All right. So let's just start with an example here. Um, all right. So let me take a sequence. Oops. Let's start with a sub n is 2 over 4n plus 1. Oops, that was supposed to be a 1. All right, so let's just start listing out terms of this series. So let's just list out, say, 4 of them. That's, I think, good enough for government work here. Huh? I did sort of watch the debate. I was helping moderate the Twitch watch party that Dr. Drury was hosting. Um, huh? The debate was getting toxic. The Twitch chat wasn't. We had one troll, but we were able to deal with him pretty easily. So, no, actually, the Twitch chat was relatively civil. Um, the debate itself, on the other hand, huh? Yeah, that was a train. It was a train wreck. Uh, yes. Mm, yeah, basically. I think there was a difference, though, that these were two very different old guys. Um, so, yeah, it was a train wreck. I mean, basically, after the very beginning of it, Trump had his 2 minutes, and then Biden had his 2 minutes. And first off, I think Biden flubbed it in the very beginning. Right? He did not bring up the things he should have brought up, but whatever. Um, yeah. So anyway, all right. So what terms do we got here? All right. So what's the first one? Huh? 2/5. Yeah. Okay. Um, what's the next one? 2/9. Then okay, and finally, said the humbug. Do you get it? No. Did anybody read the Phantom Toll Booth when they were kids? Yeah, it's a kids book. All right. All right. So is this sequence converging? Probably. And if so, what do you think it converges to? I'm going to guess 0, right? Okay. So this sequence, in this case, converges to 0 because the limit as n goes to infinity of 2/4n plus 1 is, well, 0, right? Why is it that? Because what's the power of n on top? 0, because there isn't an n, right? So it's a constant. And on the bottom, it's 1. The bottom is heavier, and so that thing's going to go to 0. We could do L'Hopital's rule or something, but it's not necessary here. Actually, no, L'Hopital's rule wouldn't apply, would it? Because what's the limit of the top? 2, not 0 or infinity. So L'Hopital's rule, off the table. Okay. It was a trap. Yeah. So, okay. So, right. Now, what I want to do is I want to make a new sequence out of this old sequence. Okay. Um, and the new sequence I'm going to define is I'm going to define S1 to be A1, which is the 2/5. Okay, so the first term of this new sequence is the same as the first term of the old sequence. Okay, no big deal. The next term, however, will be the first two terms added together. Okay, now, what is 2/5 plus 2/9? Well, exactly, right. We're going to have to do some, right, we'd have to do some fraction foo. For right this instant, I don't care. Let me just leave it as 2/5 plus 2/9. Okay, and, huh? Oh, yeah, it's not 4/14. Yeah, which is the American answer. Um, and those of you who are at home, that's funny because 9 out of 7 Americans struggle with fractions. Um, no, it never does. Yeah. It's kind of how I feel when I am up in Lafayette and I drive by Fifth Third Bank. Like, I'm sorry, but a bank that's name is an improper fraction, huh? Okay, that makes more sense. But then why do they use 5/3 as a logo? Then they should have said Fifth and Third Bank or something. Yeah. Uh-huh. Probably the latter. Uh, yes. Yeah. Yeah. It just depends on where the moon is relative to the Earth and its orbit about the sun. Yeah. If you want to learn about that, take some physics or a spherical trig class with me next year or something. So anyway, all right. So 2/5 plus 2/9. For the moment, I'm not going to bother simplifying this. We'll let the computer do some of the work for us. Um, because it's going to start to get ridiculous if we do more of this. Huh? Yeah, well, if only you weren't in class where I have a very limited window of time, right? Okay, so do we get the idea here? What's the next term? It's just going to be the first four terms added together. S5 would be the first five terms, and so on. Okay, now this S thing is a sequence, right? And like with other sequences, we can ask, does the S sequence converge or not? Okay, it either does or it doesn't. Um, and it might be the case, perhaps not shockingly, that the behavior of the S sequence is in some way going to depend on the behavior of the A sequence, right? That the two are sort of linked. And that makes sense because we defined the S sequence in terms of the A sequence. So there's probably going to be some sort of relationship there. Okay. All right. So let me pop over to Mathematica just for the sake of computation. All right. So I want Mathematica, window capture here. Okay. So I just want to use this to basically just for number crunching so we don't have to sit around and get common denominators all day. Um, all right, so what I'm going to do is I'm going to find a function, um, and it was 2 over, what was it, n, 2n plus, or 4n plus 1. Okay, great. So that's the thing. And then what I want to do is I'm going to define um, g of n. No, I can't use this. To be the, huh? Oh, I'm sorry. Yeah, there we go. Okay. So actually, you know what? I'm going to make this K instead of N, um, which it doesn't really matter, but um, oops. Um, and then hang on one sec, because why is K from 1 to N? Oh, okay. I guess I'll just do it this way. This is fine. Let me delete this. Okay, so I just care here about the numeric values, and I'll have it display it in decimal rather than in fraction form just for convenience. So the question that I want to ask basically is, what happens? Well, uh, the first term, S1, right, was just what? 2/5. That makes sense, right? So I've got 0.4, 2/5. Right, what's the next term? It would be 2/5 plus 2/9, which is, right, 0.6, 2, 2, 2, 2, 2, 2, 2, and so on, okay? All right, well, let's just continue this, okay? Right, so if I add the first 6 terms, I get, 1 point whatever. What do you guys think the end behavior is here? Yeah. Yeah, okay. So the S values are definitely increasing monotonically because the we're adding each time, and the terms that we're adding are all positive quantities. But as Cole points out, uh, 2 over 4k plus 1, as k gets really big, what happens to the size of the next term that we add on? It's getting really small, okay? All right, so you think it converges based on that? Okay, reasonable guess. It turns out it actually diverges. I must need to just check my battery. Okay, and to kind of see that, let's do something ridiculous. Like, let's go out 1,000,000 terms. Well, it's Mathematica. Of course, it's really quick. Plus, I've got a beastly computer here. Well, actually, that computer is much more beastly, right? This guy, 8 cores of. No, of course not. Uh, in the sense, well, okay, every series. Yeah, okay. No, because if every series diverged, we wouldn't really have a whole lot to talk about, would we? So, yeah, this one happens to diverge, but it diverges why? Well, because think of it, a series is really a special kind of sequence. It's a sequence that's built out of another sequence where you add the terms, right? That sequence, the series sequence, could converge, it could diverge. It's a sequence, right? And so the question we want to answer, and this is going to be quite a minefield, is under what circumstances do these series converge or not? Well, so the tricks that are going to be up our sleeve is to sort of classify what kind of series is this, or does it look like a series that I've seen before, but maybe it's just tweaked a little bit, or is it a special kind where I can do some trickery? Okay, so that's sort of the idea as to what we're going here. So the series diverges if this S sequence diverges. All right, now let me go back to the iPad for a minute. And so what I'm going to define here is Sn is going to be the sum Oops. Oops. Okay, so we defined that Sn is the sum of the first n things in our sequence, a whatever, okay? And Sn is a new sequence. Well, like any sequence, we could ask what's the limit of that thing as n goes to infinity, and we will write the series k equals 1 to infinity to mean that limit, whatever it may be. Now, that limit could converge, it could diverge. And the question, the big question, is how do we tell? Okay? There's a bunch of tests and stuff, exactly, right? So, based on the form of a sub k, and we'll look at a lot of different categories of terms there, we'll try to classify different situations and figure out, based on how they look, whether or not they converge or not. Okay? All right, so does that kind of make sense? The idea where we're going here? Okay, so an infinite number of mathematicians walk into a bar. Okay, it's a big bar, very big. Okay, the first mathematician walks up to the bar and he says, "Bartender, I'd like one beer." And the bartender pours him a beer. Off he goes. The second mathematician walks up to the bar and orders, he says, "Bartender, I would like half a beer." The bartender looks puzzled and pulls out a glass and fills it half full and says, "Okay, fine, weirdo." The next mathematician walks up to the bartender, and orders 1/4 of a beer. And the bartender's starting to get annoyed at this point, and so he pours 1/4 of beer, sends the guy on his way. The next one comes up and orders how much beer? 8. Okay, right. So uh, the so what should the bartender have done? I kind of messed up the joke. The second mathematician walks up to the bar and orders half a beer, and he says, "You idiots!" Pours the second beer and leaves. Like goes out and has a cigarette. Okay. So why is this funny? Oh, because of my delivery. Okay. Well, here's what I want to ask, right? What is, if I define a sequence, and I'll start this sequence with 0 because that's fine, right? 1 over 2 to the 0 is just 1, right? Then what I'm asking is really, what is the sum? Okay, and I claim that that sum is 2. Hmm? Okay. So this is a series, right? It's a series built out of the sequence 1 over 2 to the n. So the terms of the series or the terms of the sequence, a sub n are 1, 1/2, 1/4, 1/8, and so on. Okay, so what would the terms of the series be? 1, 1 plus a half, 1 plus a half plus a quarter, 1 plus a half plus a quarter plus an eighth, okay, and so on. Okay, so maybe the better way I should have framed the joke is, how much beer does the bartender eventually pour? Yeah, okay. You had to bring in physics. Yeah, well, yeah, okay. So anyway, oh, it's Professor Dunaway has joined us. He says the bartender isn't an economist, so he's on the Twitch chat. Yeah, um, yeah. Okay. So anyway, So our question then is, what does this converge to? And I claim it converges to 2. Now, we could mess around with Mathematica like we did a minute ago and kind of see numerically that, you know what, 2 seems reasonable. Okay, so let's just do that real quick and kind of see that I'm not lying to you here. So let me change my sequence to 1 over 2 to the um, k, and then I'm going to start my k here at 0 instead of 1. It doesn't matter. Okay. Oh, I had to run that first. Okay. So g of 0 would be the first term, 1, then 1.5, then 1 3/4, then 1 7/8, and so on. Okay. So if I go out to the 1000th term, well, okay, that's why. Okay, it rounded. Okay, so, huh? Well, there's a reason this. Do you know how much money the college spends on the license of Mathematica every year? No. It's about 30 grand a year for the college. Okay, right. And it was like 20, low 20 something grand. And then we added the Mathematica online part, and that added 15% to whatever we were paying. But yeah, we basically pay 25 to 30 grand a year for this thing. Okay, so that means 2 things. One, it's a sophisticated program because we're paying a lot of money to the people who've been developing it, and they've been doing so since the 80s. And 2, damn it, we're going to get our money's worth. Okay. Um, yeah. Okay. So point being, it's basically 2, but just shy. Okay. And I'm going to prove that it actually is 2 in the limit. Okay. So again, numerical evidence. This time we're really thinking, 2 seems pretty reasonable as the limit. Okay. But let's prove why that's the case. Okay. So the way I'm going to do this is I'm actually going to shift the question a little bit. And I'm going to say A sub n is 1 over r. Well, let's see, how do I want to do this? Oh, I need to go back to the, yeah, 1 over r to the n. Okay, n equals 0, 1, etc. Okay, so um, my first, so my term here, Sn, would be 1 over 1 plus 1 over r plus 1 over r squared plus dot dot dot. Okay. Okay, is that cool? So I'm just substituting here. Um, or actually, you know what? I'm sorry. I want to write this a slightly different way. Um, it'll make the algebra a little bit more convenient in a moment. Okay, so what's r in this case for us? It's 1/2, right? So I'm really just thinking of it as 1, 1/2, 1/2 squared, 1/2 cubed, 1/2, and so on. And writing it this way, what I had before wasn't wrong. The algebra would just be a lot more convenient this way. Okay. As we'll see in a minute. Okay. Um, all right. So the thing I need to do next um, is I need to do some funny algebra here. All right, and to motivate this, let me back up a second, okay? And let me just say, what is 1 plus r cubed? Do you guys happen to know a way to factor that? Kim, do you know? Okay. Um, or, well, okay, maybe I'm just writing it in a different order. Um, same. Okay, sorry, I need a minus here. Hang on one second. Okay, that's what I wanted. Not plus, but minus. Uh, okay, so how many of you guys saw that back in algebra? Okay, it's a difference of two cubes. Well, while we're on this subject, let me actually scoot that down and make room for um, a uh, make room for this one. You guys definitely know, right? The difference of two squares. All right, 1 minus r, 1 plus r. And I've written it in that order just for convenience. I mean, I could have put the r to the whatever first, but I've deliberately chosen this order because it'll make the pattern more obvious in a minute. Okay, good? Gucci? Okay, so um, how many of you guys saw the 1 minus r cubed ever in high school? Okay, did you remember that factorization? Okay, here's how I remember it. Okay, it was I was teaching high school kids over the summer when I was in graduate school in like a summer like upward bound program, and this sort of factorization came up one day, and so I wrote it out for them, and they're like, "Oh yeah, it's soap." I'm like, "What are you talking about? So what does soap have to do with this?" And they said, "Well, same opposite always positive." And I was like, "Oh, that's brilliant." Right? So what's the sign here? If I replace the 1 minus r cubed with a plus, so if this were a plus, this is the same sign as that. This is always opposite of that, and the last one's always positive. Well, we are. But if I had a sum of cubes, well, it's always positive. The term. Yeah, the r squared term always has a plus in front. Same opposite, always positive. Okay. So anyway, I thought that was really cool, and I'm like, I am totally stealing this, and you guys get credit. So thanks to my Upward Bound class. If any of you happen to be out there listening, this was the Upward Bound class of what, 2007, something like that. Not long after you guys were born. Yeah, you were wee kindergartners. Yeah, building sandcastles, and what else were you doing at 6? Integration. Yeah. Okay. All right. Well, this pattern continues. And if you don't believe me, couldn't you multiply out the stuff on the right? Not really. Okay. And if you think about it, well, what's 1 times everything? The stuff. Okay. And what's minus r times everything? Well, you're going to get for each, what 2 terms aren't going to cancel out? The 1 times the 1 term and the negative r times the r cubed term. Everybody else is going to cancel, right? Leaving, as I've written, 1 minus r to the fourth. Yes? Nah, now we're on to something. Suhop, they're all positive after that. Yeah, at this point, we give up the coming up with acronyms and just do the damn math. Um, yeah, exactly. So 1 minus r to the n, if I carry out this pattern, is 1 plus r squared plus dot 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 plus r to the n minus 1. Okay, because uh, if I had 1 minus r to the fourth, that takes me out to r cubed in the sum part. Okay, And so that's the general pattern. And these things happen to be called cyclotomic polynomials, but that's okay. All right, so anyway, what we were examining this. Okay, because that was a term in our series, right? 1 plus a half plus a quarter plus and so on. I'm just using R here instead of a half, right? And based on what we've seen, this is equal to that, right? So I just took the line up above and I divided both sides by 1 minus R. Cole, you look puzzled. Yeah, it's just algebra, bro. Mm-hmm. You know, you're not allowed to say that.
Why not?
It is what it is.
Yeah. It is what it is. Have you seen the meme?
No.
Oh.
Is this a meme based on oh, well.
It is what it is.
All right, so what do you guys buy that fact that I just divided that both sides by 1 minus R, so I now have this thing, right? Where's my stick? Okay, Cole just said the ones and the R's canceled, so yeah, no, they do not. Yeah, okay. So, well, what we were considering, what we wanted to know was what's the limit as n goes to infinity of this term on the left? Well, if this term on the left is equal to the thing on the right, then if I want to know what the limit of the left-hand side is, I can instead consider what's the limit of the right-hand side. Yes? Okay, so I could do that, right? Now we just have a limit to take. Well, the brilliance here is that the limit on the right is something that we can get our hands on. The limit on the left, well, A, that was the original question, but B, I don't know, with all those pluses in there, then, you know, it's not obvious what's going to be happening. Okay, so this limit, whether or not it converges, all depends on which part of that fraction. Well, the n certainly matters, but the n sitting on top of an r. So the r to the n term is really important. Okay, the ones go to 1, well, big shock, and the negative r in the bottom goes to negative r, also big shock, because those are constants, right? So the term that we need to worry about is r to the n. Okay, and then the rest of it will just sort itself out. Okay, so question. Yes, Jack. Okay, so it depends on the value of r. So if r was a half, like it is in our beer example, what does 1/2 to the n go to? Definitely 0, right? Because a half, a quarter, an eighth, and so, right, definitely converging to 0. But what about if r were like 3? That's basically what's about to happen. Yeah, it's a bigger than 1, less than 1 situation. But uh, if r were 3, we'd have 3, 9, 27, 81. That feels pretty divergent to me. I don't know about you, gentlemen. Okay. What about if r is equal to 1? 1, 1, 1, 1. Okay, that's a problem. Okay. But we'll deal with that problem separately. Okay, so r equals 1 is an issue, and what about r equals -1 for that matter? Well, okay, don't look at the line up above it. Just think of r to the n. What happens to -1 to the n? It just flip-flops between -1, 1, -1, 1. Is that sequence converging? No, okay, because it's flip-flopping. So it diverges because it fails to converge. Okay, that's the definition of diverging, right? All right, but what about if I had something like -2? Well, then I'd have -2, 4, -8, 16. Same problem. It's going to blow up, right? So that one diverges also. Okay, so this limit converges. That limit converges precisely when the um, the value of r is less than 1 in absolute value. Okay, because if we said to like -1/2, well, it would alternate, but it would still squeeze in on 0, right? Because you'd have a half, -1/4, an eighth, -1/16. Yes, it's bouncing plus minus, but it's still, I mean, if you'll, those of you who are at home can't see my awesome like air waves going on here, right? Okay, anyway. Hmm? So, well, because what's the limit of a constant sequence? 1, 1, 1, 1, 1. Okay, right. No, I'm talking about this limit right here. So I'm talking about this limit so that we can then consider that limit up above it. Okay, but for right now, right this instant, I'm just thinking about the limit of r to the n. Okay, um, all right. So if r is less than 1, then the limit that we were really interested in it's equal to that. Because if r is less than 1, then what does the limit of r to the n converge to? 0, right? So then here I would have 1 minus 0 over 1 minus r. Okay? What do you get if you plug r equals a half into that? One minus a half, 1 over that is 2, which is how many beers I said the bartender poured. Yeah? It's totally true. Yeah, it is. This is math class, not real life, right? Yeah. Well, in a limit, right? Because we're dealing with infinities here, right? So the bartender joke is it's exactly that, a joke, right? No human bartender could actually get to 2, right? But if we think about this mathematically, then yeah, that happens. Okay. Now, maybe a better way to explain sort of why we need to worry about this sorts of stuff. How many of you guys have ever heard of my buddy Zeno of Ilia? Yes, Jack, you've heard of Zeno? Yeah. So there's a door right there, right? For me to get to the door, I first got to get halfway to the door. Well, for me to get to the door, I got to go halfway the remaining distance. So I'm never going to get there, right? All right, see ya. All right, you guys teach yourselves. Uh, okay, so yeah, right. This is the math and the real world are not the same thing. Yeah. Okay. All right. So anyway, R is a half, we get 2, which was the punchline to the beer joke, right? If R were some other value, then you just plug it in. Okay. Now, why did I leave out the case where R equaled 1? Well, because what would happen if I plugged in R equals 1 to this fraction? Uh, yeah, yeah. You don't divide by 0. Okay. Blow up. Okay, but let's take the R equals 1 case separately. What we're really doing is we're looking at the series that. Okay, so here a sub n equals 1, and s sub n would equal n, right? Because if I add n copies of the number 1, that's called the number n, right? What's the limit as n goes to infinity of that thing? Yeah, sorry, the limit of Sn, not An. The limit of An is clearly 1, right, because it's constant. But the limit of the sum of all those guys is infinity. Okay, so this guy big time diverges. Okay, because what's the value of that limit? N equals 0, right? Or 1. It doesn't matter where we start this one, but for the other ones, I started at 0 for convenience. Yeah, it's almost like the bounds of an integral. Okay. Um, it's just what's the starting value of n, and then the top number is what's the ending value of n. And if it's infinity, then right, really what we mean is a limit. But yeah, okay. All right, so that series diverges. So, moral of the story, the series that we were interested in converges if the r is between -1 and 1, so less than 1 in absolute value, and it diverges otherwise. This kind of sequence or series has a very special name. Any guesses? Yeah, thank you. It's called a geometric series because it was built out of the geometric progression where you multiply by a constant ratio every time. Okay, that's the number r, hence why I used the letter r. Okay, so yeah, so this thing is called a geometric series. Now, you have to be very careful when you use this because you can conclude garbage if you use the 1 over 1 minus r formula erroneously. For example, this, correct? Okay, so if you said, oh, that's equal to 1 over 1 minus 2. Well, what's wrong is this step right here. So this formula saying that the series equals 1 over 1 minus r requires that r be less than 1 in absolute value. Okay, so if this equal sign right here, let me circle it so that everybody at home can see. This equal sign right here is the bullshit equals. Okay, it's not equal. But if I erroneously said it were, like uh, in error,
Oh.
right? It's an adverb form of error.
Okay.
Okay, so the equals, the red equals there is the bullshit equals,
Mhm.
right? Okay, now why is that bullshit? Well, yes, of course it's bullshit because it's wrong. But okay, let's like forget the fact that I know it's wrong. Like, why is it just looking at what I've written patently bullshit? That's too complicated, Will. That's also too complicated. That's still too complicated. What am I doing? I'm adding up a bunch of positive numbers. And you mean to tell me that if I add up a whole bunch of positive numbers, I get a -1? Bullshit, right? Math don't work that way. Yes, you've probably seen a number file video about this thing in the past. Okay, yes. In complex analysis, there is a sense in which this ought to be -1, but it's not equal to -1, okay? Because then you're talking about poles in the complex plane and the analytic continuation of functions and a lot of complicated stuff that you're not ready for yet, okay? So, yes, that is to say, you're not ready for those mysteries of mathematics, okay? All right, um, so you have to be careful when you use this 1 over 1 minus r trick, because if you use it in a situation that it's not permitted, you're going to get garbage. Okay, this is similar to what happens if you apply L'Hopital's rule to a problem where L'Hopital's rule doesn't apply. Well, it doesn't work, but you get answers that are just total garbage, right? And that makes me a sad panda. Okay, so don't do that. Why am I panda? It's from South Park, right? The sad panda. I'll explain later. Okay. Anyway, um, so that's the geometric series stuff. Okay. Um, and uh, we should probably quit here because it's 9:55. Okay. All right. So we'll continue with this discussion. Yeah, of course, Dr. Dunaway got that reference, the sad panda reference. That makes me not a sad panda. It makes me a happy panda. Huh? No. So, all right. Well, so we'll continue with this discussion on Friday, and I'll have to pick up the pace a little bit, but we'll make it. So, all right. Thanks for playing. Have a good day. Rest of your day, guys. Wear your masks. Don't be stupid. And I'll see you guys on Friday.